I was talking about the moderate minimum, this roughly 70-year period where there were virtually, almost no sunspots observed. And we're really not sure why that occurred. One thing that we do know is during that period, Europe and North America reported particularly cold winters. And in fact, some people go as far as to say there was a little mini ice age during that period. And, again, we don't know why this happened, and we really don't know why it would have affected the weather on Earth, the number of sunspots. That's something that's still of great interest to us, because, if this kind of thing, another Maunder minimum, were to occur, we would like to be able to predict that and be prepared for something like that. Very, very cold winters, if it does happen again. All right, let's keep moving. So sometimes when we look around near the sun, we see solar flares. These are actual eruptions, coming off of the photosphere. When hot, this hot plasma that is part of the sun just rises up and erupts, and sometimes these things can extend way out into space. This one in this particular picture here is curling back in on itself. Sometimes they do, sometimes they don't curl back in on themselves. And these are sometimes called solar prominences. And there's large, if a large amount of material comes flying off of the sun, that's actually called a coronal mass ejection. That's one of the things that SOHO does. The observatory is, if there is a coronal mass ejection and it happens to align with where the Earth is going to be, right? Because it would have to be in the direction that the Earth is heading. The coronal mass ejection, by the way, does not travel at the speed of light, because it's actual matter. It travels very fast, but it doesn't travel at the speed of light. Anyhow, if it's going to hit the Earth, a lot of times there'll be warnings specifically for satellites, right? Satellites can go and there are literally thousands upon thousands of communication satellites. This is part of why we can pick up the phone, pick up our cell phones and talk to just about anybody on the planet at any one time. Anyhow, those satellites, if you're given enough warning, will go into kind of a shutdown mode where you want to protect the sensitive electronics from these coronal mass ejections. So they'll either turn away from the direction of the sun, or in some cases they can actually they have like a protective outer casing, and they'll enclose themselves in that protective outer casing. All right, so that's just a little about our modern. Oh, and actually, there are some times that these prominences are so strong that it'll actually affect not just our satellites around the Earth, but they'll affect there'll be like large blackouts. I think there was one, I forget exactly what year it was maybe a decade or two ago. It was actually in Canada. It caused power outages, huge power outages, because of something that happened on the sun. So these are, what I was just talking about. These are these solar flares. All right. Okay. So. All right. So that is a solar flare. And here's the thing about coronal mass ejections. Okay, so this is when you have this large material bubble, if you will, and it detaches from the sun itself and escapes into space in all directions. It doesn't just happen. They're actually showing you some of these coronal mass ejections in this picture. But the real concern is if this material happens to be aimed towards where the Earth is going to be. We try to protect ourselves. I mean, we have some protection. That is, of course, the Earth's natural magnetic field protects the Earth from these are usually charged particles, and the Earth's atmosphere. Not the atmosphere. Well, the atmosphere protects a little bit too, but the charged particles will spiral around the magnetic field lines, and they'll either crash into the North Pole of the Earth or the South Pole of the Earth. And of course, when those charged particles, so this doesn't have to be a coronal mass ejection. This is just any material that's coming from the sun. I mean, there's always, particles coming from the sun. If they're charged and they get trapped in the Earth's magnetic field, once those charged particles hit the atmosphere is much closer to the Earth. Like in this picture, it would be very, very close to the Earth. I mean, it barely extends up 100 miles, and the Earth's magnetic field extends out more than 1,000 miles. Right. So anyhow, when those charged particles hit the Earth, or hit the atmosphere of the Earth, they heat up, and that's in fact what they call, the northern lights or the southern lights, the aurora borealis for the northern lights, the aurora australis for the southern lights. All right. So this is just about the solar wind. So these are that's a daily occurrence. There's material coming from the sun all the time. Again, most of it is charged particles. And of course, we can see this in the X-ray images of looking at the sun. Changes along with sunspot cycles. So the corona is affected by the sunspots. And of course, the corona is, as it says there, more irregular at sunspot peaks. So that's that 11-year cycle. Let's see. Oh, this is so the 22. Remember, the one thing I wanted to point out, and I meant to say this in a video, the last video. This 22-year cycle, you would never know that it was 22 years, right? Unless you had equipment that could detect the polarity of the magnetic fields, right? So basically there is an 11-year cycle, and it's 12 years when you think about the polarity of the magnetic fields, like in the northern hemisphere of the sun and the southern hemisphere of the sun. Anyhow, so here are some possible correlations that have been seen, but not very well understood. Solar flares and coronal mass ejections ionize the atmosphere. They tend to disrupt electronics, and of course, if there are astronauts in orbit, like on the International Space Station, that if we know that there's a coronal mass ejection or a solar flare that happened, Houston will tell the astronauts to stay within the International Space Station to avoid direct exposure to this. This is highly charged particles. I mean, you wouldn't want these things hitting the human body. It would not be good. All right, the heat. Let's see. In the heart of the sun, the sun's mass and energy production, we find that on average, every kilogram of the sun produces about 0.2 milliwatts of energy. So this isn't much as it says here. I mean, you might say, okay, well, that's not that big of a deal. That doesn't seem like that big of a deal. In fact, if you were to look at a gerbil, milliwatts, remember that's times 10 to the minus third watts, 0.2 times 10 to the minus third. A gerbil, it would actually be producing more and by the way, watts is power. Energy power is energy per unit time. Anyhow, so how is this even possible? And how is it that the sun, is producing this incredible amount of energy? Remember, we saw before that the luminosity of the sun is equivalent to about 4 times 10 to the 26th watts. And of course, it's been doing this for 4.5 billion years, and we expect it to go another 5 billion years or so, for the complete solar cycle. And so, what about it? What about it is what's going on? How is it producing such tremendous amounts of energy and doing it in a nice, steady fashion? You don't want a star that's undergoing explosions or anything like that. For life to evolve, it takes an enormous amount of time, right? I mean, the Earth, of course, has been around for 4.5 billion years. You want the sun to be as stable as possible for that to take place. So how is that taking place? And of course, it's because the sun undergoes nuclear fusion. All right, so nuclear fusion, we'll go through the steps of this. This is actually a very complicated area of physics, by the way. But that's how the sun basically converts matter into energy. So when 2 protons come together, they will basically, it's complicated, right? Actually, what happens, but the basic idea is the 2 protons, which repel each other, they don't want to be near each other, with given high enough temperature and a high enough density, will slam into each other and will fuse, and then so they become one particle, right? 2 protons, and then of course 2 neutrons join that to produce a helium nucleus, right? So that's the basic idea. When that happens, the input mass is a little bit more than the output mass, right? So all the things that go into the nuclear. So this is a nuclear reaction. It's not a chemical reaction. It's happening at the nucleus. When that happens, there's a little bit of energy left over, because this third nucleus and is a little bit smaller in mass than the sum of everything that went into it, and so that little bit of energy comes from that loss of mass. Remember Einstein's famous equation, E equals mc squared. Energy is equal to mass times the speed of light squared. So really that is the explanation of how the sun produces energy. The sun has tremendous amounts of matter, right? It's 2 times 10 to the 30th kilograms. That 4.5 billion years ago, there was a little bit more than that, and so the whole time, basically, what's been going on is this tiny little reaction. So it is very tiny. That's the whole idea of the little gerbil wheel thing. But there's enough matter in the sun for that to produce this tremendous amount of energy each second that we know about. So that's there's Einstein's famous equation. Mass can be thought of as frozen energy, if you will. Energy, when you convert matter into energy, then you get this tremendous amount of energy. Just a small amount of matter contains a tremendous amount of energy. Right? And you can kind of see that in this equation, because you're multiplying by c squared, the speed of light squared. So you get this tremendous amount of energy. This is Einstein's famous equation. All right, so basically the idea is the sun is losing mass, but it's turning that into energy. But it's not. It seems like the sun is losing. It's losing tons and tons and tons of kilograms each second, but the sun is a very massive